Now, in this lecture, we'll find out the length of chord BC. In the drawing, we have a semicircle. We know that the center of this semicircle is at this point, point O. Inside the semicircle, we have square DEFO, and we know that the area of square DEFO is equal to 5 square units, and our mission is to find out the length of chord CB. So, first of all, we know that all the angles inside any square are right angles. Therefore, those 4 angles are right angles. So, write it down. This angle equals to 90 degrees. This angle is also equals to 90 degrees. This angle equals to 90 degrees. And this angle equals to 90 degrees. And you know that the area of this square DEFO equals to 5 square units. Here the squared brackets is the sign for the area. It means the area of square DEFO equals to 5 square units. And we know that the area of any square, if we have a square if this is a square, then the area of this square equals to the length of the square times the width. This is the area of this square. The length times the width, but because of the fact that the length and the width are the same, you can write down that the area of any square, that is to say, all the sides of any square are equal to each other. Therefore, the area of any square equals to the length, that is the side, times the width, that is also the same side. That is to say, the area of any square equals to the side of the square squared. Therefore, the area of square DEFO equals to the side of the square squared, and we know that the area of this square DEFO equals to 5 square units, so we can substitute the area by 5. So 5 equals to the length of one side squared here we will take a root out of this equation. We get that the length of one side of square DEFO is equal to the square root of 5. That is to say, all the size of square DEFO equals to, each side equals to the square root of 5 units. In the next step, we will join points D and O together by a straight line. By joining points D and O, we actually created here right triangle DFO. The green triangle DFO is a right triangle because angle DFO equals to 90 degrees. It is one angle of out of 4 angles of the square, and all the angles are right angles. So I copy the green right triangle DFO in a new page, and we will implement the Pythagoras theorem on this right triangle DFO in order to find out the length of the hypotenuse DO. So actually, this is the right green triangle DFO that I copied from the original drawing. Side DF equals to side FO. They are both equals to the square root of 5 units. And we want to find out the length of the hypotenuse DO. So we will use the Pythagoras theorem in order to find out the length of the hypotenuse DO. So here by PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of the right triangle DFO is DO, therefore the square of the hypotenuse is DO squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to DF squared plus FO squared. Okay, so DO squared, that is the square of the hypotenuse, must be equal to DF squared. DF equals to the square root of 5 units. It is one side of the square. Therefore, DF squared will be equal to the square root of 5 squared plus FO is also equal to the square root of 5. Therefore, FO squared equals to the square root of 5 squared. So DO squared equals to the square root of 5 squared, it is of course equals to 5, plus square root of 5 squared is 5. The conclusion is found out that the whole square, that is the square of the hypotenuse, equals to 5 plus 5, that is 10. Here we'll take a root out of this equation and we'll get that the whole, that is the length of the hypotenuse, equals to the square root of 10 units. Okay, the whole equals to the square root of 10 units. DO is the hypotenuse of the green triangle, DFO. But in addition, what is the definition of DO? Line segment DO starts from point O, that is the center of the semicircle, and ends at point D, that is the point on the semicircle itself. This is exactly the definition of a radius. Therefore, DO is the radius of the semicircle, and we found out that the O equals to the square root of 10 units. That is to say, the radius of the semicircle equals to the square root of 10 units. Likewise, if we focus on line segment OB, line segment OB starts from the center of the semicircle, that is to say from point O, and ends at point B, that is the point on the semicircle itself. This is exactly the definition of a radius. Therefore, OB is the radius of the semicircle, that is equal to the square root of 10 units. And likewise, if we focus on line segment AO, line segment O starts from point O, that is the center of the semicircle, and ends at point A, that is the point on the semicircle itself. Therefore, OA is the radius of the semicircle, that is equal to the square root of 10 units. And in the next step, I will present to you a new rule, and we'll implement the new rule in our drawing. According to the new rule, rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. I write it down, the sum of the angles on one side of a straight line is equal to 180 degrees. I will explain what is the meaning of rule number 1. According to rule number 1, if we have a straight line where AB is a straight line, and we have here on the straight line AB any point, we'll choose this point and we will define it as point K. Here we have side KN. According to rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on the upper side of the straight line AB at point K, here the sum of the angles must be equal to 180 degrees. So which angles we have in the upper side of AB at point K? We have this angle CKL plus this angle LKA or AKL. In total, the sum of those two angles must be equal to 180 degrees. According to this rule, rule number 1. And the same thing is true about the lower side of the straight line AB. If you focus on the lower side of the straight line AB, here this angle must be also equal to 180 degrees. We can implement this rule number 1 in our drawing. Why? Because in our drawing we know that this is a semicircle, and AB, it is the diameter of the semicircle. AB is the diameter of the semicircle, must be a straight line. So AB is a straight line. So if you focus on the upper side of the straight line AB at point O, here the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of AB at point O? We have this angle that is equal to 90 degrees plus the missing angle. We define it as angle X. In total, they must be equal to 180 degrees. So according to rule number 1, if we focus on the straight line AB, it's point O, on the upper side of point O, or if we focus on the upper side of the straight line AB at point O, the sum of the angles must be equal to 180 degrees. So in the upper side of AB at point O, we have this angle that is equal to 90 degrees plus the missing angle X. In total, they must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and we'll get that the missing angle X equals to 180 degrees minus 90 degrees. It is equal to 90 degrees. So we found out that the missing angle equals to 90 degrees. That is to say, it is a right angle. So here, the missing angle equals to 90 degrees. Okay. And because of the fact that angle EOB, this angle is a right angle, therefore triangle EOB must be a right triangle. So we can implement the Pythagoras theorem on the right pink triangle EOB. So I copy the right pink triangle in a new page, and we implement the Pythagoras theorem on this right pink triangle EOB. This is the right big triangle that I copied from the original drawing. Triangle EOB. We'll implement the Pythagoras theorem in order to find out the length of the hypotenuse EB. So here by PT is a version for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is EB, therefore the square of the hypotenuse is EB squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to EO squared plus OB squared. According to the Pythagoras theorem, EB squared equals to EO squared plus OB squared. So EB squared is the missing side, so we leave it as it is. EB squared equals to EO squared. We already found out that EO equals to the square root of 5 units, therefore EO squared equals to the square root of 5 squared plus OB squared. OB equals to the square root of 10 units, therefore OB squared equals to the square root of 10 squared. So in conclusion, we found out that EB squared, which is the square of the hypotenuse of the right triangle EOB, equals to square root of 5 squared, it is 5, plus square root of 10 squared, that is 10. In conclusion, we found out that EB squared equals to 5 plus 10, that is 15. Here we will take a root out of this equation and we will get that EB equals to the square root of 15 units. So we found out that EB equals to the square root of 15 units. Here EB equals to the square root of 15 units. Our mission is to find out the length of this chord called CB. We already found out that EB equals to the square root of 15 units. The only thing that is left to find in order to find out the length of CB is to find out the length of line segment CE. In order to find out the length of line segment CE, we will make a construction. We will complete this semicircle to a circle. The first step So in the first step we completed a semicircle to a circle. In the next step we will extend line segment EO on both sides, in the upper side and in the lower side. Here we will extend line segment OE towards the upper side of the circle until it touches the circle. So we'll extend line segment OE until it touches the circle. We define the touching point of the extended line segment OE in the circle as point M. We'll extend also the lower EO towards the lower side of the circle. We'll extend line segment EO by straight line in the lower side of the towards the lower side of the circle until it touches the circle. We'll define the touching point of the extended line segment EO in the circle as point N. So here what is the definition of line segment ON? O is the center of the circle, N is the point of the circle itself. Therefore ON is the radius of the circle and the semicircle also. Therefore it is equal to the square root of 10 units. And what is the length of EN? Here EN, from the drawing it is very easy to see that EN equals to EO plus ON. EN equals to EO plus ON. That is to say, EN equals to EO, that is square root of 5 units, plus ON, that is square root of 10 units. So in conclusion, we found out that EN equals to the square root of 10 units plus square root of 5 units. Square root of 10 units plus square root of 5 units. Likewise, we find out the length of line segment ME. From the drawing, it is very easy to see that the length of line segment ME is equal to MO minus EO. MO minus EO. That is to say, ME equals to MO. Point O is the center of the circle. Point M is the point of the circle itself. Therefore, MO is the radius of the circle and the semicircle. That is equal to the square root of 10 units minus EO. EO equals to the square root of 5 units. In conclusion, we found out that ME equals to the square root of 10 units minus square root of 5 units. In the next step, I will present to you a new rule and we will implement the new rule in our drawing. It will be rule number 2. According to rule number 2 is true in any circle. So I'm writing down that in any circle if we have this circle, that will be any circle. And we have chord AB. This is called AB inside the circle. That intersects with chord CD. This is called CD. And the intersection point of the two chords is defined at this point. We define the intersection point as point O. So, if chord AB intersects with chord CD at point O, again, if chord AB intersects with chord CD at point O, then the following equation will be true. Then AO times OB will be equal to CO times OD. Okay, AO times OB equals to CO times OD. We can implement rule number 2 in our drawing. Why? Because in our drawing we have chord MN. This is chord MN that intersects with chord CB. This is chord CB at point E. The intersection point between the two chords is defined at point E. Therefore, according to rule number 2, we get that ME times EN equals to CE times EB. So I copy again the drawing in a new page, and only with the two chords that intersect with each other, and we implement rule number 2 in our drawing. So chord MN passes from the center of the circle, that is to say from point O. Chord MN intersects with chord CB at point E. Repeat again. In our original drawing, chord MN intersects with chord CB at point E. Chord MN intersects with chord CB at point E. Again, chord MN intersects with chord CB at point E. Therefore, according to rule number 2, we will get that the following equation is true, that ME times EN, ME times EN equals to CE times EB. ME times EN equals to CE times EB. We've already found out that ME equals to the square root of 10 minus square root of 5. We have already found out that EN equals to the square root of 10 plus square root of 5. We have already found out that EB equals to the square root of 15. The only missing line segment is line segment CE. This is according to rule number 2, of course. So we'll put the data inside the equation and we'll get the value of CE. ME equals to the square root of 10 minus square root of 5. EN equals to the square root of 10 plus square root of 5. And it is equal to CE, that is equal to, this is the missing line segment, so we'll leave it as it is, times EB. EB equals to the square root of 15. Here we have square root of 15 minus square root of 5 times square root of 10 plus square root of 5. We can write, because of the fact that A times B equals to B times A, we can write it, we can change the two expressions by each other. That is to say, we can write square root of 10 plus square root of 5 times square root of 10 minus square root of 5. That is equal to CE times square root of 15. Here we have this expression, square root of 10 plus square root of 5 times square root of 10 minus square root of 5. We'll find the value of this expression according to the algebraic identity that states that A plus B times A minus B equals to A squared minus B squared. Now, specific expression, A equals to the square root of 10 and B equals to the square root of 5. And this expression equals to A squared minus B squared. Therefore, if A equals to the square root of 10, it means the square root of, if A equals to the square root of 10, it means that the square root of A is 10, A squared minus B squared. If B equals to the square root of 5, it means that B squared will be equal to 5. So in conclusion, we found out that A squared minus B squared in our specific expression equals to 10 minus 5. And according to rule number 2, this expression equals to CE times square root of 15. In conclusion, we found out that 10 minus 5 equals to CE times square root of 15. 10 minus 5 is 5. So 5 equals to CE times square root of 15. Here we will divide this expression by square root of 15. And we'll get that CE equals to 5 over square root of 15. So actually we found out that the missing line segment CE equals to 5 over square root of 15. And what the line segment that we are looking for, the chord that we are looking for is CB. What is the value of CB? It is very easy to see from the drawing that CB equals to CE plus EB. CB equals to CE plus EB. So we just, again, CB equals to CE plus EB. we just right now found out that CE equals to 5 over square root of 15, and we already found out that EB equals to the square root of 15. So in conclusion, we found out that the chord that we are looking for, CB, this chord CB equals to 5 over square root of 15 plus square root of 15. Here we will simplify this expression because we don't want that we have square root in the denominator. Therefore we will multiply square root of 15 by square root of 15, and then we will divide it by square root of 15. That is to say, we will multiply square root of 15 by 1. Any number that is multiplied by 1 remains the same number, it doesn't change, so it is allowable to do it. So CB equals to 5 over square root of 15, and again we will multiply square root of 15 by square root of 15, and then we will divide it by square root of 15, so we change nothing. So CB equals to 5 plus square root of 15 times square root of 15 is 15 over square root of 15. So in conclusion, we found out that CB equals to 5 plus 15, 20, we have 20 in the numerator, over square root of 15. Again, we don't want to have a square root in the denominator, therefore we will multiply this expression by square root of 15, and then we will divide it by square root of 15. So CB equals to 20 over square root of 15 times square root of 15 over square root of 15. So CB, the chord that we are looking for, equals to 20 times square root of 15, and square root of 15 times square root of 15 is 15. Okay. Here we will divide both the numerator and the denominator of this expression by 5, and we get that CB, the chord that we are looking for, the length of the chord that we are looking for, equals to 20 over 5 is 4, so in total in the numerator we have 4 times square root of 15 over 15 over 5 is 3. In conclusion, we found out that the length of the line segment that we are looking for, that is to say CB, is equal to either 4 times square root of 15 over 3 units, or in terms of numbers, it is equal to 5.164 units. Okay? So in the next step, I will summarize the lecture. In the original drawing, we add a semicircle. We know that the center of the semicircle is at this point O. Inside the semicircle we have square DEFO, this square, and we know that the area of this square is equal to 5 square units. Our mission is to find out the length of this chord called CB. So because of the fact that DEFO is a square, we know that in any square all of its 4 angles are right angles. So those 4 angles that is inside the square are right angles. Each one of them is equal to 90 degrees. And we also know that the area of any square, if this is a square, the area of the square will be equal to the length of the square times the width of the square. But because of the fact that the length is equal to the width, you can write down that the area of this square equals to the side of the square times the side of the square. That is to say, the area of this square equals to the side of the square squared. We use this formula in order to find out the length of one side of square DEFO. We know that the area of square DEFO, this square, is equal to 5 square units, so we can substitute the area by 5, and know that the area of any square equals to the side squared. Therefore, the area of our square that is equal to 5 must be equal to the side squared. We took a root out of this equation and we found out that one side of square DEFO equals to the square root of 5 units. So here, actually, all the sides of this square are equal to square root of 5 units. Okay? In the next step, we join points D and O together by a straight line. By joining points D and O by a straight line, we created here the green right triangle DOF. So I copied the green right triangle DOF in a new page and we implemented the Pythagoras theorem on this green right triangle DOF. This is the right triangle DOF that I copied from the original drawing. We know that side DF equals to side FO. They are both equal to the square root of 5 units because of the fact that they are the length of the side of the square. And here we will implement the Pythagoras theorem in order to find out the length of the hypotenuse DO. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is DO, therefore the square of the hypotenuse is DO square, and it must be equal to DF square plus FO square. So DO square equals to DF square, DF equals to the square root of 5, therefore DF square equals to the square root of 5 square, plus FO square, FO also equals to the square root of 5, therefore FO square equals to the square root of 5 square. So in conclusion, I found out that DO square equals to the square root of 5 square is 5, so the square root of 5 square is 5, so DO square equals to 5 plus 5, that is 10. We took a root out of this equation and found out that DO, the length of the hypotenuse DO, equals to the square root of 10 units. And you can write down that DO, the length of the hypotenuse DO in the right triangle DOF equals to the square root of 10 units. But DO, it is not only the length of the hypotenuse in the right triangle DOF, but it is also the radius of this semicircle. Why? Because it starts from the center of the semicircle, that is to say from point O and ends at point D, that is the point on the semicircle itself. Therefore, DO is the radius of the semicircle that is equal to the square root of 10 units. What is OB? Line segment OB starts from point O, that is the center of the circle, and ends at point B, that is the point on the circle itself. Therefore, OB is the radius of the semicircle, that is equal to the square root of 10 units. For the same reason, OA is also the radius of the semicircle. Why? Because it starts from the center of the semicircle, that is to say from point O, and that's at point A, that is the point of the semicircle itself. Therefore, OA is the radius of the semicircle, that is equal to the square root of 10 units. Okay. Then I presented to you a new rule, and we implemented the new rule in our drawing. According to the new rule, the sum of the angles on one side of a straight line is equal to 180 degrees. So if AB is a straight line, we choose any point on the straight line AB, for example point K, and we have here side KL. According to rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on the upper side of the straight line AB at point K, in the upper side of AB at point K, the sum of the angles must be equal to 180 degrees. That is to say, the sum of those two angles must be equal to 180 degrees. Or angle angle, this is angle actually AKL, this angle AKL plus angle BKL. This is angle BKL plus this is angle AKL. In total, the sum of those two angles must be equal to 180 degrees according to this rule number 1. The same thing is true about the lower side. If we focus on the lower side of the straight line AB at point K, here this angle must be also equal to 180 degrees. We can implement rule number 1 in our drawing. Why? Because in our drawing we have we know that this is a semicircle according to what is given as the question, and AB must be the diameter of the semicircle. So AB is the diameter of the semicircle. It is absolutely a straight line. So if we focus on the upper side of the straight line AB at point O, the sum of the angles on the upper side of AB at point O must be equal to 180 degrees. So which angles we have on the upper side of AB at point O? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees according to rule number 1. So 90 degrees plus the missing angle, this is the missing angle. In total, they must be equal to 180 degrees. This is according to rule number 1. So we subtracted 90 degrees from this equation, and we got that angle x equals to 180 degrees minus 90 degrees, that is 90 degrees. So we found out that angle EOB, this angle equals to 90 degrees. If angle EOB equals to 90 degrees, it means that the pink triangle EOB, it is a right triangle, therefore we can implement the Pythagoras theorem on the right triangle EOB. So I copied the right pink triangle EOB, the new page, and we implemented the Pythagoras theorem on this right pink triangle EOB. This is the right pink triangle EOB that I copied from the original drawing. We know that EO equals to the square root of 5 units, OB, that is the radius of the semicircle, equals to square root of 10 units, and the only thing that is left to find is to find out the length of the hypotenuse EB. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is EB, therefore the square of the hypotenuse is EB square. It must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to EO square plus OB square. So in conclusion, according to the Pythagoras theorem, we will get that EB square equals to EO square plus OB square. So EB square equals to EO square. EO equals to the square root of 5, therefore EO square equals to the square root of 5 square plus OB square. OB equals to the square root of 10, therefore OB square equals to the square root of 10 squared. So in conclusion, we found out that EB square equals to the square root of 5 squared, that is 5, plus the square root of 10 squared is 10. So in conclusion, we found out that EB square equals to 5 plus 10, that is 15. We took a root out of this equation and found out that EB equals to the square root of 15 units. So the hypotenuse EB equals to the square root of 15 units. And here also we can find out that EB equals to the square root of 15 units. So we actually found out the length of EB. We are looking for the length of chord CB. So the only thing that is left to find is to find out the length of line segment CE. In order to find out the length of line segment CE, we completed the semicircle to a circle, and then we extended line segment OE to the upper side until it touches the circle at point M. Then we extended line segment EO towards the lower side of the circle until it touches the circle at point N. And then I presented to you rule number 2, and we implemented rule number 2 in our drawing. According to rule number 2, that is true in any circle, if chord AB intersects with chord CD at point O, point O is the intersection point of the two chords, then the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can actually implement rule number 2 in our drawing. Why? Because in our drawing we have chord MN that intersects with chord CB at point E. Okay, so I copied the two chords that intersect with each other in a new page here. Chord MN intersects with chord CB at point E. Therefore, according to rule number 2, we will get that ME times EN equals to CE times EB. Again, ME times EN equals to CE times EB. We have already found out that ME equals to the square root of 10 minus square root of 5, EN equals to the square root of 10 plus square root of 5, and EB equals to the square root of 15. The only line segment that is missing is CE. So we substituted ME by square root of 10 minus square root of 5, we substituted EN by square root of 10 plus square root of 5, and we substituted CE as the missing line segment, we substituted EB by square root of 15. Then we changed the sides of this expression according to the rule that A times B equals to B times A. Therefore, square root of 10 minus square root of 5 times square root of 10 plus square root of 5 equals to the square root of 10 plus square root of 5 times square root of 10 minus square root of 5, that is equal to CE times square root of 15. Then use the trigonometry and the algebraic identity that A plus B times A minus B equals to A square minus B square. In our specific expression, A equals to the square root of 10, B equals to the square root of 5. And this expression, A plus B times A minus B equals to A square minus B square. What is A square minus B square in our specific expression? If A equals to the square root of 10, it means that A square equals to 10. So it is A square minus B square. And if B equals to the square root of 5, it means that B square equals to 5. So in conclusion, we found out that A square minus B square in our specific expression equals to 10 minus 5. And 10 minus 5, according to rule number 2, equals to CE times square root of 15. 10 minus 5 is 5, so we found out that 5 equals to CE times square root of 15. Then we divided this equation by square root of 15 and found out that CE equals to 5 over square root of 15. Here the missing line segment CE equals to 5 over square root of 15. What is the length of CB? CB, it is very easy to see that CB equals to CE plus EB. Okay? Here, the length of the chord that we are looking for, that is to say CB equals to CE plus EB. We have already found out that CE equals to 5 over square root of 15 and EB equals to the square root of 15. So the answer to the question is that the length of the line segment, the chord that we are looking for, CB equals to 5 over square root of 15 plus square root of 15. Here we simplified this expression by multiplying square root of 15 by square root of 15, and then we divided it by square root of 15, so we change nothing. Because anything that is multiplied by 1, it doesn't change. So here we have CB equals to 5 over 15 plus square root of 15 times square root of 15 over square root of 15. So CB equals to 5, and square root of 15 times square root of 15 is 15 over square root of 15. 5 plus 15 is 20, so in the numerator we have 20. So in conclusion, I found out that CB equals to 20 over square root of 15. Then we multiply this expression by square root of 15 and we divide it by square root of 15, so we change nothing in order to eliminate the square root in the denominator. So we found out that CB equals to 20 times square root of 15 over square root of 15 times square root of 15 is 15. Here we divided this expression, both the numerator and the denominator of this expression, by 5. 20 over 5 is 4. So in total, in the numerator we have 4 times square root of 15. In the denominator we have 15 over 5 is 3. So we found out that the length of this chord CB, the chord that we are looking for, it is equal to either 4 times square root of 15 over 3 square units, or in terms of numbers, it is equal to 5.164 units. Okay, thank you very much.